Welcome to your first calculus video. In these videos, what I'll be doing is going through many of the ideas from the chapter that we'll need. Now, this means we will also spend some time lecturing in class, but hopefully we can keep this to a minimum so you can spend more time doing problems. In this video, I'm going to go over the ideas from section 1.1, as well as a little bit of how to use these videos to make the most out of them. Some things to notice are right here on the top here. We've got the section we're in, graphs and models. So if you ever open up a video and you say to yourself, that looks familiar, I feel like I've already done that, maybe you've clicked on the wrong video. And if you think none of this makes any sense, maybe you need to go one video back. Next, what will be listed is your in-class problems. So for tomorrow, you should try to work on problems 8, 22, and 77 before you come to class. We will go over those problems in class as well as any questions anyone has. Now, it's very important that you actually do these problems. Math is not a spectator sport. You probably know at least one person in your life who loves to watch football. They probably watch football all the time. They watch college football, high school football, professional football, and I'm willing to bet that all that watching has not helped them get much better at football. What you really got to do is you really got to get in there and play and practice. Same thing with math. Watching people do problems is not going to be useful, really not going to learn a lot from it. What really matters is you getting in there and trying them yourselves. Now, I'm not saying you got to bring these in, they're going to be perfect every time. You just have to bring in a real honest, being honest with yourself attempt at these problems. Next, we've got listed the homework problems. These problems will be due on Friday, and they're going to be pretty similar to ones we've done, but a little bit extra. And if everything goes well, you should have time to actually start on these in class. You can get your questions answered. The next key feature of all these videos are going to be the keywords. So at the beginning of each video, I'm going to list the words that you need to be looking out for as you take notes. So an important thing I said there is, as you take notes. You should really be taking notes. You don't want to watch this video again, I'm guessing. So what you need to do is you need to get your notebook out now and start writing all of these words down. You might want to even write these down at the beginning of your notebook so you can summarize, and when you look back in your notes, you know where to look. Another nice thing is that once I say the word intersection, you know that we're probably almost done because there's only one more keyword left in the video. As you watch this video, you should also be thinking of questions you have. A good part of class time is going to consist of us going over problems and going over questions people have. You should always try to think of an original question you have, but sometimes you'll have the same question as someone else, and that's just fine as well. So in Chapter 1, we're going to be reviewing some ideas that you should already be familiar with that we're going to use over and over again in calculus. Now, I'm not saying that you remember how to do them all exactly. That's why we're reviewing them. I know it's been probably 3.5 months since most of you thought about math, and that's fine. That was summer vacation. But now we're getting back into it, and so we're going to spend some time with these. If we go over anything in Chapter 1 that you have never seen before, you need to come and see me immediately, or you need to find a tutor, or you need to find a really good friend that you're going to be able to talk to about this stuff. Because Chapter 1 is going to be words and ideas that come up over and over and over again, and if you don't understand them now, it's not going to get better without some work. But anyways, here we go. So our first word is graphs. So our story begins in 1637 with a man named René Descartes, and here he is. A pretty dapper looking guy for his time. And what he studied was he studied two very different things. He studied algebra, which was very concerned with the equations like x squared plus y squared equals 1. Equations are interesting because you can manipulate them with your mind. But he also studied geometry, which is interesting because this is the world we see with our eyes. If we look out our window, we see triangles, circles, squares, shapes, etc. And what he had an idea was very different at the time, is that these two things could be used together. That is, if we started with an equation, maybe we could make a shape out of it, and if we had a shape, maybe we could make an equation out of it, and so these ideas should really go back and forth and really help each other. And so he came up with this crazy idea that what we can do is we can use the solutions to this equation and make a picture out of them. And so what Descartes did was he said, well, let's look at our equation here and let's make a little table of our x and y values. And what we can do is we can say, well, if we put 0 into our equation, then y has to equal 1 in order to make our equation true, so that 0 squared plus 1 squared equals 1. If we put 1 in for x and 0 in for y, well, that also works because 1 squared plus 0 is equal to 1. Let's see, we can also do 0 into negative 1, negative 1 into 0, and a whole bunch of other stuff. And if you keep going, if you keep trying to make all possible points that'll make this, you'll end up with a huge table, lots and lots of numbers. The problem is that this isn't very useful. It's very difficult for a person to look at numbers, or a table of numbers, and make any sense out of it. We're pretty visual people. So instead what we need to do is we need to find a way to make this into a visual object. And so Descartes invented graphing. So here we have our first big blue box, and I'll give you a hint. Anything in a blue box should be written down and memorized. It's very, very important. So our definition here is that for any equation, any point making the equation true is called a solution point. The set of all solution points of an equation is called the graph of the equation. So on our previous page, we had ourselves the equation x squared plus y squared equals 1, and we said that we have a particular solution point at 0, 1, because if x equals 0 and y equals 1, then 0 squared plus 1 squared equals 1, so our equation is true. And if we collect every single one of these together, we can build the graph. And so what I've pictured over here on the right is our graph of our equation. What we do is we label our axes, so this is a number line called the x number line, and we also have the y number line. And if we want to find the point 0, 1 on our graph, what we need to do is we start at the origin, we go 0 in the x direction, so we don't move left or right at all, and instead we just go 1 unit straight up, and we put a point there. So the one point we found so far is up here on the graph. And as it turns out, every single other point along this entire circle here, if we figured out the x and y numbers they represent, we'd be able to put them into our equation, and they would work. We'd get a true equation. Now, of course, this is tedious and time-consuming, and so luckily we have computers and calculators that do most of the graphing for us. Pretty rarely am I going to ask you to graph something that we know the equation of in this class, but we will want to graph other things. It is important, though, to appreciate the different perspectives we have when thinking about things, though, and they give them different names. So whenever you deal with equations, we're going to say that's thinking from an analytic perspective. When we have graphs, we'll say that's either from a graphical or geometric perspective. And finally, sometimes we're going to think from a numerical perspective. A numerical perspective is very common in science. What you do is you have a table of values that you know work. So for instance, we have 0, 1, 1, 0, negative 1, 0, 0, negative 1 are some values that we know give solutions to this equation. But all three perspectives are very useful, and we'll use them throughout the course. So now we're on to intercepts. An intercept is going to be a special type of solution point that has 0 as either its x or y coordinate. These are the points on the graph that intersect the x or y axis. These are respectively called the x-intercept or y-intercept and have the form a0 and 0b respectively. Okay, so take a minute, pause the video, write that all down, and then we'll talk about what these really mean. So what this really means is that basically, horizontally here, we have ourselves the x-axis, and what we can see on our graph is we have these 2 points here on our graph that hit the x-axis. These are called x-intercepts. So if we have the graph visually, we can say, well, it looks like this is at negative 1, 0, and the one over here is at 1, 0. And this is okay, this is a good approximation, but if we have ourselves an equation and not the graph, we can do it very exactly to figure out exactly where they are. And it's not so bad. The key feature is to notice that to get x-intercepts, our y values are going to be 0. Similarly, to get our y-intercepts here and here, where we hit the y-axis, we again need to notice that our x values are 0. So there are two tests for these, and they're pretty much the same. So our test for x-intercepts is pretty easy. Step 1, we set y equal to 0 in the equation. Step 2, solve for x. These solution points, if any, are your x-intercepts. So our example of this is, since our equation is x squared plus y squared equals 1, well, okay, step 1, we set y equal to 0. So now we have x squared plus 0 squared equals 1. Step 2, solve for x. Well, x squared equals 1 means that x is equal to, key thing here to remember, since we have x squared equal to 1, this means that x is going to be plus or minus the square root of 1. So we're really going to get two answers here. We're going to get x values of -1, and it's a y-intercept, so y is 0, and an x value of 1 and a y value of 0. Now I want you to take a second and think if you can guess what needs to change to do the test for y-intercepts instead. And hopefully you figured out that the test for y-intercepts is pretty similar, except we just set x equal to 0 and solve for y. I'm not going to do this, but it's not too bad. You should get 0, 1 and 0, -1. So the next step on our journey is to review how to find points of intersections of equations. So previously we looked at how to find where a graph of an equation intersects the x-axis or y-axis, and now we want to think about where two separate equations might intersect. So the definition is that the point of intersection of two equations is the set of all points that are solutions to both equations. That is, these are going to be the points that we can plug into both of the solutions, and they both make the equations true. Now to find these solutions, there's several ways to do it. I'm going to review one way to do it that usually works here. If you have another way that works, that's fine. You don't have to use my way. I'm just going to review one here quickly. So we're going to suppose that we want to find all points of intersection of x plus y squared equals 3 and y minus x equals -1. So the first step is that, if possible, graph both equations in order to determine the approximate number of intersection points we should be looking for, if any. Some people think of this as a cheat, because if you're just going to graph it, you can probably use the trace feature to figure them out anyways, and I agree, you could do that. But this is also a good time to practice some of our algebraic skills that'll be very useful later on in calculus, where we won't be able to graph things. So for now, graph and check, but we're also going to do a lot by hand. So here's our graph. The blue line in the graph corresponds to our second equation, and the red arc corresponds to our first equation. And we can see that it looks like what we're going to be looking for is 2 points of intersection. So the next step is to solve one of the equations for one of the variables. Often it doesn't matter, you just kind of pick one and go for it. Usually what you want to do is you want to look for the equation that maybe has one easy variable and one tough variable. So in this case I'll choose the one underlined in red, x plus y squared equals 3. And I will solve it for x. So what I'll end up with is x is equal to 3 minus y squared. Step 3 says to substitute the previous equation into the other equation and attempt to solve this equation. I agree that this is probably grammatically not the clearest thing, but if I show the steps, I think you're going to see how this works. So in the previous step, we solved for the red equation. So in this step, we're going to start with the blue equation. That's our other, whereas the red is our previous equation. And now what we want to do is we want to take all our values of x, we only have one of them in this case, but all values of x, and replace them with the 3 minus y squared. And so this part is just coming from our y value, or x value in the previous step. And now what we want to do is, now that we've got an equation that's just down to one variable, it's only in terms of y's, we can use our standard processes we learned back in algebra in order to solve this. So I can see there's a squared term, so it's a quadratic. So I'll probably want to move, everything to one side of the equation clean this up a little bit algebraically. And so cleaning this up, what I can see is I now have a nice quadratic function, y squared plus y minus 2 equals 0, and as it turns out, this one's actually going to factor. And so what we're left with then are two y values, y of 1 and a y of negative 2. And the last thing we need to do is we need to actually find the points. So now what we've done is we've identified the y coordinates here, but we still need to find the x's. And we can do that by putting these y values into either one of the equations. So in our final step here, what we're going to do is we're going to pick whichever equation we think looks the nicest. I think x plus y squared equals 3 looks nice. So now we replace y with 1, and we have x plus 1 equals 3, so x equals 2. So this means one of our solutions is going to be 2, 1, and in a very similar way we can use negative 2 in the equation in order to find our other solution, so that when y is negative 2, we get an x value of just negative 1. And so we can see that in our graph we've got both of these points would be exactly what we got if we traced our graph or if we looked very closely, but overall these are our solutions and we found them algebraically. So congratulations, you've made it to the last definition in the first video, mathematical models. So a mathematical model is an equation or graph of an equation that represents actual data. It can also be represented by a table as well. Mathematics has a history of being concerned with practical things, you know, like how much fuel should I put in my car in order to go a certain distance, how strong a material should I make bridges out of, but also is concerned with very fun things like what are the solutions to this equation that really doesn't occur in the world. And both of these are very useful, but if you're a scientist in the room, you're probably concerned with more the mathematical model. That is, how does this help me work with actual data? So we're going to be spending all semester working with this. We'll go back and forth between the very abstract equations and the very concrete, useful data-driven equations, but it's a good thing to be aware of that a mathematical model is anything that makes an attempt to represent actual data. And always, 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 the problem with mathematical models is we always strive to ride this line between simplicity and accuracy. Very simple, easy-to-use models are often very inaccurate, but very accurate models tend to be very, very difficult. So let's look at an example of one. Well, before we look at one, let's actually look at our magic word for today. It's bumblebee. This will be very useful as you take your first WebWork quiz when you're done watching this video. So please remember that the magic word is bumblebee. So here is our first example of a mathematical model. We'll refer to it again and again. And if you've ever gone traveling in a foreign country, you've probably needed to convert from temperature in degrees Celsius to degrees Fahrenheit. And a quick way to do this is using what's called the traveler's formula. You take your temperature in degrees Celsius, you multiply it by 2, add 32, and you're going to end up with a Fahrenheit temperature. So as an example of this, if it's going to be, say, 0 degrees Celsius outside, we use the formula. We take 2 times 0 plus 32, and we end up with 32 degrees Fahrenheit. So 0 degrees Celsius, the point where water freezes, is the same as 32 Fahrenheit, where water freezes. The formula seems pretty good. Now there's also the actual formula, though. The actual formula is slightly different. In order to convert from Celsius to Fahrenheit, we take our Celsius temperature times 9/5 plus 32, and that will get us the actual way to convert temperature. Now the traveler's formula is pretty easy. Multiplying by 2, pretty easy. Adding 32, not so bad as long as the number you get isn't so bad. Multiplying by 9/5, however, takes a little bit more brain power, takes a little bit more work, and what you get out of it isn't really necessarily worth it when you go traveling in a foreign country. So let's look at a table here to see some examples. So in this table we've got some temperatures in Celsius along the top row, the traveler's formula, and the actual formula. So if you wake up and you watch the weather and you see they tell you it's going to be 0 degrees out today, well, the traveler's formula would give you 32 and the actual temperature is 32. It's going to be cold. If they tell you it's going to be 10 degrees out, well, that means 52 Fahrenheit according to Traveler's formula, or 50 according to the actual formula. Well, it's going to be in the 50s, not so bad. Similar with 20 degrees, you're either going to get a 72 or 68, both still pretty nice light jacket weather. Maybe you could even get away with shorts. If it's going to be 30 degrees, well, it's going to be hot. 92 and 86 are pretty close. So this Traveler's formula, it's pretty simple, it's fairly accurate, and it's not bad as long as we're only concerned with temperatures we expect people to actually face as they go about their daily business. However, this is not a good formula to use if you're a scientist doing things at very high or very low temperatures. And we can see this better with the graph. So in our graph, what we have is along the horizontal axis, we have temperatures in C, and along the vertical axis, we have temperatures in degrees Fahrenheit. Our Traveler's formula is given by the green line up here, and our actual formula is given by the purple line. And what we can see is as long as we stay in the narrow range of -20 to say 30, maybe even 40 degrees, is that these lines are very, very close together. There's not much difference, and you can use either formula pretty interchangeably. However, as the temperature gets warmer, we can see that they start to disagree more and more and more, and they start to get a little bit off. So this model is very, very good, very useful for these small range of temperatures, but if you're going to do things at millions of degrees Celsius, I actually don't even know if that makes sense, ask a physicist, let's say thousands of degrees Celsius, then you're going to want to use a more accurate formula and go through the detailed computations of multiplying by a fraction. But we will talk much more about modeling in class throughout this semester. So congratulations, you did it! You made it through your first video successfully, and now you have 3 more things to do. The first thing to do, post a question to the document on Blackboard. So right beneath this video there's a little document you need to click and open. It's going to open a spreadsheet, and you need to write a question there. If you see someone's questions you agree with, or you think it's a really good question, it was your question, put your initials to the right of it. That way I know, sort of where the class is at. Also, you're going to need to take a quick web work quiz. So it's going to be a quick quiz that asks you some basic questions just to see if you were paying attention during the video. Like all web work stuff, you can take it as many times as you need until you get them all right, up until class starts. And finally, work on problems 8, 22, and 77 on page 8 in the textbook. So these are the questions that we're going to spend time going over with in your groups tomorrow. And what you want to do is you want to get these done, because once you get these done, then you can start working on the homework ones, which will be due on Friday. But as always, if you have any questions, let me know in class, in office hours, or an email. Have a good night.